Okay, this is for you guys that were gone. You can see you've got two different screens going here. One's the TV screen back there, one's this screen. And this deals with the first segment of Igneous Rock Lecture for the Earth scientists that were gone. We've finished up the minerals portion of our study of the solid Earth. Now we're going to cover the part of the Earth that deals with rocks. So now we're going to look at the minerals and how they form rocks. And we'll go ahead and get this thing started here. I'm going to hide this. I'm going to go up here and get the power started. Change some settings here. Duplicate show. Away we go. So I'll kind of turn this way so you're not looking so much at the TV. Like I said, you're going to want to take notes over this because you will eventually be quizzed on this and tested. So real quick, and I'll go fairly quick. If I'm going too fast for your note taking, you could always slow me down by hitting the shift and back arrow, or speed me up by hitting the shift and forward arrow. So to start with, you want to know your rock cycle, because all rock on Earth, we believe, well, I'll go to the first screen because this is what I talked about, Chapter 5, Igneous Rock. We got two different types of igneous rock here. We have granite, which is basically the foundation of Mount Rushmore and what the faces are carved out of. And then we've got, basically, this isn't basalt, but we've got a chunk of gabbro, which comes from a different type of magma. So igneous rocks can have this big variety of different types of magma that produce them. If I go down in here to the rock cycle, like it says, you should know the rock cycle. Probably something you should have had back when you were already a third grade. I'll go back into the video here. And then we kind of build on it throughout your science career. Usually we start looking at rocks in the grade schools. Then if you're lucky, you can look at them too also in the middle level. But maybe not. Maybe it's the first time you've looked at it. But all rocks basically come from three different types. We have igneous, sedimentary, and metamorphic rocks. We're going to say that igneous rocks are the formation of pretty much all rocks on Earth, because at one point in time, the Earth was essentially a big molten ball of material that eventually cooled off and crystallized into rocks. Now, as time has gone on, weathering processes have broken those rocks down into sediments, which can reform into sedimentary rocks. I can take an igneous rock or a sedimentary rock, and I can, through heat and pressure, change it into something called a metamorphic rock. But igneous deformation, or the breakdown of igneous rocks, is the formation that produces all rocks on Earth. So that's kind of the foundation of what we're talking about. Here we've got a picture of Devil's Tower. Devil's Tower is a big, huge, what we call igneous intrusion that's located in northeast Wyoming. If you've ever been to it, it's kind of this neat 870-foot tall structure. You can walk around the outside. It's columnar jointed basalt, or it's actually not basalt, it's columnar jointed faunolite, which is a type of igneous rock that's what we call porphyritic. So it's got different sized grains in it. If I look at a piece of Devil's Tower up close, you're going to see it's got big crystals and little crystals of different size, which means it cooled at different rates. And it's actually a type of igneous rock we call faunolite, because you can hit it with a hammer and actually make it ring. But anyway, all igneous rocks at one point in time were a liquid magma either below the surface or above the surface that eventually solidified, cooled off to form rocks. And depending on the cooling rate, you're going to have different crystal sizes. So the big thing that we break igneous rocks into is we base it off of two things. One is texture, and the other one is going to be essentially like color. So texture, if you remember it, and in your worksheet 4.1, I think it was, we talked about how crystal size is based on cooling. Slow is big. So slow makes them grow, whereas fast, you don't get any crystal size. So the faster you cool an igneous rock, or I should say a magma body or a lava body, the faster you cool it, the smaller the crystals, the slower, the bigger. So it's the most important property in identifying an igneous rock is going to be the crystal size. So if I look at this, you can see the crystals of this piece of granite are big. Whereas if I take a look at this piece of andesite, the crystals are pretty small. So that suggests different cooling rates. we have different types of texture. The first one we're going to talk about is going to be phaneritic or plutonic. The second one is going to be extrusive or amphinitic, or what we call volcanic. All three of those terms mean the same thing in each case. Pyroclastic, just like if somebody is a pyro, it's like they like to play with fire. Pyroclastic means it comes from fire, like a volcano. 4, glassy, just what it implies. It looks like glass. And then 5 is going to be fragmental, which is a bunch of fragments that have been welded together through the heat of a volcanic eruption. So that's the textures. If we go through each texture individually, phaneritic texture means fat. In other words, you have great big fat crystals, like in this case, the piece of granite that we looked at before, big fat crystals. Here's another big fat crystal piece of granite. Here's a piece of gabbro. You can't really see it here, but it's got big crystals in it that you can see. So phaneritic texture rocks, like in the case here, you got 2 chunks of granite. You carve it up, polish it up, put it in the countertops, and it looks kind of pretty because you can see all the different types of crystal structures in that rock. To make a phaneritic texture, you're going to have a magma chamber at depth. In other words, it's below the surface quite a ways. The magma only made it so far up, it didn't ever break the surface, but the magma chamber started to cool off. And as it cooled, the crystals were able to form, in some cases over thousands or possibly millions of years. The crystals, in the case of a phaneritic rock, you can see them, like in the case of these rocks here. You've got hornblende and biotite and quartz, and you got some pink orthoclays here and some plagioclays, so you can see the individual crystals. We can also call this intrusive or plutonic because it forms in the interior of the Earth. Pluton, think of like a lava lamp where you've got the plutons of magma trying to get to the surface, but they don't quite make it, and then they start to cool off and form a rock. The next type of texture we call is amphinitic. Amphinitic basically means fine or tiny. So in the case here, we got a picture of basalt, and we got a picture of, looks to me like probably rhyolite, I'm guessing. Amphinitic is fast cooling. So to get amphinitic texture rocks, we're going to have fast cooling of the magma at depth usually, but sometimes, no, not at depth, excuse me, near the surface. So you're not going to necessarily see the individual crystals in an amphinitic because they're so small. Like I said, it's near surface, not deep. Near surface or at surface, where the magma cools off quickly. We can also call this extrusive rock because it's extruded from a volcanic vent, but it's not explosive necessarily. We can also call it volcanic because it comes out of a volcano, so that's amphinitic. The third type of texture we call pyroclastic, and if you'd have been in class today, I would have thrown one of these pyroclasts at you. Pyroclastic texture, we tend to call them volcanic bombs. It's like they're bombs coming out of a blowing up volcano. So you got a piece of probably rich in basalt bomb there. Here you got a piece of rich in silica. This is pumice, and this is probably just some mafic bomb. But the reason you get pyroclastic is because you got a lot of gas trapped in a magma. It makes the magma really explosive. So then the material comes blasting out of there in chunks. In some cases, the chunks are kind of part molten, and they start to rotate, and they form these football-shaped like pyroclastic things. All pyroclastic things tend to be full of holes, so we call them vesicular, just like blood vessels, veins that run through your body. It's like you've got vesicles or vessels that run through the rocks where the gas was trying to escape when it was solidifying. The next thing we're going to talk about is glassy texture. Glassy texture, most famous glassy texture rock is obsidian. I'll go get a chunk. Hang tight. I got this big giant chunk of obsidian. I actually have a fair amount of obsidian throughout the classroom. Obsidian forms when you have magma that cools really fast, or lava, excuse me. It can be magma, but typically it's lava. In the case of this chunk of obsidian, most obsidians, they actually form from high in silica rhyolitic type magma. So it's like, well, how come this white rock can produce something that's black like this. Not all rhyolites are this color. Sometimes they can be kind of reddish too. But this is almost pure silica oxide like glass. It's just that all it takes is just a few atoms of iron or magnesium to change the color in here to this black color. It's kind of like I told the kids in class, it's like if you go to the paint store and you want to get some purple paint for your house because you like purple. If you go and get the purple paint, the base color for almost all paints is this goofy white color. So it's like this. But all it takes is this magma, which flows really, really slow, to come in contact with a body of water. And then all the silica that's in there cools rapidly instead of slowly. I mean, really, really rapidly. And then there's a few iron chunks in there, like 5 to 10 parts per million, that change the color to black. You can get obsidian in lots of colors, blue, kind of a butterscotch color. There's mahogany, which is a mix of different colors. There's snowflake. There's white. So it all depends on what's going into there, kind of like when you're mixing paint. And it doesn't take very many trace metal elements to make that silica different colors. So, but if we look at the obsidian, though, usually it's where the lava comes in contact with some sort of either body of water or groundwater. So can you find this stuff in Yellowstone? Yes, there's actually something called Specimen Ridge, I believe is what it's called, where you have big chunks of this that people used to come and steal all the time. But now they tell you, you can't be stealing no obsidian from a national park. So no, you can't do that. And the reason is because Yellowstone has lots of rhyolitic magma. That's why it makes it so explosive. But sometimes it's not exploding. Sometimes it's just moving real slow. Comes in contact with groundwater, and bam, you get obsidian to form near the edge of those rhyolitic lava flows. And it crystallizes really rapidly, and now all of a sudden you don't have any chance for crystal, or I should say it cools really rapidly, so crystals can't even form, so it just turns into like glass. The next texture we call fragmental. Fragmental comes in two forms. We have what we call welded tuff, and then we also have something that we call breccia. Welded tuff, like in the picture here, is essentially volcanic ash that when it gets ejected, there's so much heat, it welds that volcanic ash together into a rock. I've got a big chunk of pinkish colored welded tuff back here from the Strawberry Ridge eruption out of Yellowstone. It's really pretty stuff. It's pink. You can get it in lots of different colors depending on what the chemical makeup of the magma is in the explosion that the volcano it's coming out of. You can also get what we call breccia right here. Sometimes when volcanoes explode, they basically shatter the rocks around them, and the heat of the eruption along with the ash welds all the pieces together into breccia. So it gives what we call a fragmental texture. We can also call these pyroclast too. Just like anything that comes out of a volcano that's blown out of there is like a pyroclastic explosion. Last kind of thing here, we'll actually go through a couple of them here. This is a agglomerate. You can see you've got, this is a basaltic type magma flow, or at least it's high, looks like it's high in iron and magnesium. And the rocks that were part of that volcanic eruption just got fused right into the magma flow, so we call that agglomerate. The last texture is what we call porphyritic. Porphyritic is when you have different cooling rates, fast and slow. So the magma cools fast for a while, then it cools slow for a while. Like in the case of this one right here, you can see how you have different grain sizes. So we call this porphyritic. And you can see how you've got big and small crystals because you have different cooling rates. The big crystals are what we call phenocrysts, and then the small crystals are what we call the ground mass. So the stuff you can't see is the ground mass. The big stuff is what we call phenocryst. So you have magma that cools at different rates because of movement within the magma chamber, all kinds of different dynamic processes. So porphyritic texture is actually pretty common in lots of rocks that form in magma chambers too. So we could go down to the river and I could probably kick around about 15 rocks in about 5 minutes that have porphyritic texture. It's a pretty common thing. Last thing is pegmatite texture. Pegmatite is where you get big giant crystals in the rock, and the crystals have to be at least as big as your pinky, like a centimeter in length in terms of width. That's where we get like our mineral samples from. So when you're looking at like hornblende and biotite and quartz and some of those things, they actually come from pegmatitic uh, or pegmatite deposits in parts of Montana and Colorado, where you can go find these things with big crystals in them because they were formed in magma chambers where cooling was really slow. And if you're a crystal hunter and you like to find crystals, what you do is you look for pegmatites. And then you might find some cool quartz or whatever in these rocks that cool real slow. And then, like in some case, some company's going to come break it up and sell it as mineral samples. So pegmatite's kind of cool stuff, and we do have a lot of that in Montana. So there's your different textures, and I actually got a little further with you guys because I talk faster, but I do suggest you take notes over these things because you will have a quiz when you come back, when you get healthy or wherever you're at. So, but I'll share this with everybody so you have it. Okay. Have a nice day.